Okay, so we'd like to welcome everyone to PasswordsCon, to the next talk that we're having. Just a reminder, we'd like to thank our diamond sponsors, Prisma Cloud and Vanta, and our gold sponsors, Adobe and SemGrep. A reminder about your phones, please put them on silent so that the speaker is not interrupted, or anyone else in the audience. If you want to take photos of the speaker or his presentation, you're okay with that?
Sure.
He's fine with that. Please remember the policy not to take anyone else that is attending without their consent, both in here and outside. So, cracking 936 million passwords. How is that going to work? Well, we're going to have Jeff Deifik take us through that. So, Jeff, you're up.
Thank you. Can everybody hear me? Excellent. So, I'm Jeff. This is my talk. If you go to jdeifik.com or deifik.com, you can see a PDF of all these slides. So, a little bit about me. Nothing very exciting. Read at your leisure. If anybody has any questions during the talk and they're short questions, ask me. If they're long questions, save it to the end. So, there's a thing called Have I Been Pwned? You've probably all heard about it. They have a way of downloading all of their passwords. You can't download them in plain text, but you can download them hashed. So I got these in NT landman format. And 936 million. So it turns out you need a lot of RAM to crack passwords. So you can either use a CPU or a GPU. I found that a CPU worked much better. So I started off with 128 gigabytes of RAM. I upgraded to 256 gigabytes of RAM. If I had deep pockets or somebody wants to pay me $1,000, I can update to 512 gig of RAM, but that hasn't happened yet. Yeah, so if you want to do this in a time-efficient fashion, buy yourself some RAM. And I found 92% of them so far. So the tools are John the Ripper and Hashcat. Hashcat is primarily a GPU-accelerated way of breaking passwords. Turns out it didn't work especially well for me. It's a common tool. It does work. It just didn't provide a lot of passwords per second. So John the Ripper, they don't make a lot of official updates. Neither does Hashcat, but they make a lot of unofficial point releases. John the Ripper doesn't really work too well with GPUs. I don't know why. It just doesn't. The good news is that the way to break passwords is to have good dictionaries and custom-made rules or good rules. That is by far the most efficient way of finding passwords. And the other thing is they have extremely great support. Hashcat, I'm using 6.2.6, which is the latest version, 3 years old now. I was using a 3060 Ti GPU. If I used a faster GPU, it might be 5 or 10 times faster. It still wouldn't have made much of a difference. The rule syntax, so imagine you want to insert an alphabetic character in the first position. With John the Ripper, that's one line. With Hashcat, you have to have one line for each character. So now imagine that you want to insert a character in the first position, the second position, all the way through to, let's say, the 30th position. Let's say you want to insert 100 characters. So that's 30 times 100 characters. That's 3,000 lines of rules. So they say they need to do this to run quickly. Maybe it's true, but I'd rather have one line and debug one line and show you guys one line of a rule than 3,000 lines of a rule. And the dictionary attacks for Hashcat, I found were taking up a good amount of memory. My Hashcat machine had only 16 gigabytes of memory. I tried it on another machine with 120 gigabytes of memory. It just uses a lot of memory to do what it does. So word lists. I don't know if you guys download word lists. Most of them are pretty crappy. Some of them are pretty good. I found that RockU, either 2021 or the previous version of RockU, is very good. RockU 2025 I downloaded. It's very big. The quality is not so good. So when you download these things, they're full of junk. Most of them except for RockU. Some of them have lines that are hundreds of thousands of lines of characters long. Some of them have random junk in them. trying to curate something that's 10 gigabytes or 30 gigabytes is very difficult or impossible. So good quality word list is mission critical to breaking passwords in a timely fashion. So I wrote a bunch of tools to help me with this task. I wrote a program called Short, which will truncate a file and only produce the first X characters, whatever that might be. So if you have a 100,000 character line, you can knock down to 50 or something. I presume nobody's got 100,000 character passwords. I've never heard of one. There's msort, which is a merge sort routine. It needs to have more physical memory than you're trying to sort, but other than that, it works very well. What else do we have here? We have multi-merge will merge a bunch of things, so it runs quicker. I have sample, which will sample however many every 10,000 lines or things of that nature. I have things that produce line length statistics, counts of ASCII characters. I have some password utilities that I wrote, and I have sometimes when the password is found, it's got unprintable characters, and so they encode it in a hexadecimal format. I have a thing to turn it into binary stuff. It's called password on hex. I also wrote some password statistics programs to give me statistics on the passwords I found, which I'll be showing you later. So there's standard tools. GNU Sort is an excellent tool. Unique Com. I use Emacs as my text editor. I know not everybody likes it, but it will handle gigabyte files. It will handle binary data. It will handle pretty much anything. Does somebody have a question? Okay. So relative hashing speed. If you look at NT-Landman, it's the fastest hashing algorithm. That means if you want to break it, it takes the least amount of resources. If you look at DEScrypt, which is the tool I used, the password I was breaking previously, it's much slower. DEScrypt, I think it came around in 1978 or something like that. So why NT-Landman is such a fast algorithm, which means it's basically weak, I don't know. If modern Linuxes, they tend to use things like bcrypt, which is substantially slower. So if these passwords were encrypted with bcrypt, I probably would have found very, very few of them. So you should be using a hashing algorithm if you want your password to be secure that's slow, and if you want to make it easy to break, you should use one that's fast. So salt. Does everybody know what salt is? Does anybody not know what salt is? Come on, somebody's got to not know. Everybody knows it? Yeah, okay, very good. So, in 1979, people figured out if he's got a password that's password 123 and he's got a password 123, the hash is going to be the same. So he said, we're going to add, 14 bits of random data to each person's password. So the chance that his password and his password, when hashed, are going to be the same is 1 in 4,000. So the reason you do this is it makes it very difficult to do a rainbow table attack. So again, they figured this out in 1979. I'm guessing that's older than half the people in the audience. But Windows doesn't use salting. I don't know why. I've never heard anybody give me an explanation why it doesn't use salting. So that's very good for me breaking passwords and very bad from a security standpoint. So in the 80s, Unix went up to 48 bits of salt, which is a huge number. In 1996, bcrypt used 128 bits of salt. So the chance of having collision is 1 and 2 to the 128, which is a very, very big number. So good for me, NT-Landman, no salt. Those things run real quickly. So the tools I used, dictionary attacks is the most efficient way to find passwords. You just encrypt the dictionary word, you compare it to the hashed word. If they're the same, you found your thing. So the brute force attack, let's say you want to break all of the 8-character upper, lowercase, and number passwords. So that's the number of combinations. I'm not going to read it out. It took me 229 days on my 3060 Ti. I think I got like 4 million passwords that way, which is actually not a good number in terms of passwords per second. And the problem is, even if you can do that really quickly, let's assume you can do it in a day. When you go to something longer, like 12 characters, things scale up very, very quickly. And so it just doesn't matter how fast your GPU is. If you had 1 character of your password, it's going to run 30 to 80 or 100 times slower. So it does not scale. 16 character upper lowercase number, that's number, and that's how many years it would take me to crack it with my GPU, which is pretty much forever, if that's a cryptographically strong password. So the efficient way is to use a rule-based attack, which I'm going to come to next. So, I'm sorry, rainbow tables. People say, use rainbow tables. Rainbow tables are awesome. So I downloaded, what was the thing? I think it was 9 characters and upper, lower numbers and symbols. It was very, very slow. I've got the statistics here. Oh, if you want to do this, DEF CON's got the data duplication village. You bring them a 6 terabyte hard drive, they'll fill it up with rainbow tables. So the numbers are, I'm sorry, I don't have, it took a long time. I thought I put the numbers here. 1 second. Well, I'll tell you the numbers. It took, I think it was like 500 seconds to crack 1 password with rainbow tables. That's just randomly accessing a file that was stored on a solid state hard drive. So if you have 100 million passwords or 900 million passwords, it's going to take forever. So I don't know why rainbow tables took as long as it did, but it was very slow. Okay, so here's rainbow crack. So I downloaded the 9 character lowercase and alpha and spaces thing. It's 43 gigabytes. It's a good amount of space. One of the tools I was unable to get working, but eventually I found a tool. Where is it? Oh, I sent in a bug report for Project Rainbow Crack. Never got a reply. Oh, also the memory used. I figured out that if I wanted to do it the 936 million passwords, I'd need 150 terabytes of RAM. So that wasn't going to work. I don't have that much RAM. So I used with rcrack IMT. That actually worked. I was impressed. So it took 6 seconds per file. There was 84 files, 504 seconds is what it took to break 1 password. So I used the password that I knew was in that 9 character set. So if you scale that up, that's 16,000 years to try all the 9 character passwords. So I don't know why I was as slow as it was. I used a SATA SSD. If I would have used an NVMe SSD, it might have been 5 times faster, but that still wouldn't have helped me. So if you have 1 or 2 passwords, go with Rainbow Crack. If you have 100 million or 900 million, it's not going to work. So Hashcat. My machine for Hashcat had 16 gig of RAM. I decided to try it on 1 million passwords, and it took 660 megabytes of space. So assuming it scales up linearly with that, it would take 624 gigabytes of RAM to run that. So I don't have that much RAM. So I decided not to use Hashcat with dictionaries. So if you have small dictionaries or small numbers of passwords to crack, it's probably fine. I mean, 1 million passwords is a lot of passwords. So I can't really fault the Hashcat guys for using 600 megabytes of RAM. But if somebody wants to break 900 megabytes of passwords, it's not going to work. I'm sorry, 900 million passwords, not going to work. So now we get to the rules. John the Ripper has the best rules. So rules, they take a standard word from a dictionary and they modify it in some way. They have a very, very verbose set of rules. And you can make custom rules, which I did. So I upgraded my machine from 120 gig to 256 gig. And when you run this, it takes a fair amount of memory. And you can run multiple forks, which will multiply the amount of memory. So 1 fork would take, I don't know what, say 20 megabytes of memory. So 6 forks, sorry, gigabytes. So 6 forks would take 6 times that. So as the number of unfound passwords decreases, the hashing speed stays the same, but you can use more things in parallel at a time, and so you can increase the effective throughput of things. So when I first started this using the default John the Ripper rules, I managed to find 487 million passwords in 12 days. which is like half the passwords. That was pretty cool. And also, since the number of unfound passwords decreased by a factor 2, I could double the number of forks. So that was a really good thing to do. That was the low-hanging fruit. So John the Ripper has a very good default dictionary. It's very, very small. And using that, I found 154 million passwords. That was really good. So there's an incremental attack which will never, ever terminate. And it starts off pretty quick and it slows down, unfortunately, pretty quickly. So I found 320 million passwords. So these numbers are not all exclusive. These are like inclusive numbers. So they would add up to more than the individual numbers. So then I started using the RockU word list. So I found 156 million passwords that way. And then I bought the 256 gigabytes of memory so I could double the number of threads I was using, or number of forks. So I started doing attacks using the default word list and the default rules, which is all the rules. And I found another 15 million passwords that way. So just for context, using Hashcat and I think all the 9 or 10 character passwords, I found 4 million passwords in half a year of time. So this is really, really fast compared to a brute force attack. It's going to miss things. It's not going to get everything, but the speed is so fast, it's better to reduce the number of unfound passwords you have and then crank the number of forks up. So my computer has 64 cores and 128 threads. So I can scale this up quite a bit. So I started off with 7 forks, and then I said, let's apply the rules twice. So if one of the rules is uppercase the first character, the second rule might be append a number at the end. So it would take a long time and probably never terminate, but I found another 36 million passwords that way. So then I decided to not use the standard word list, but to use the RockU 2021 word list. I found 265 million passwords in less than an hour. That was super awesome. So then I was able to increase the number of forks up to 18 after I found all those passwords, and I was able to run things like more than twice as fast as before. So I found another 11 million passwords in 3 days with that. So the thing with finding passwords, you find the easy passwords first and you find them quickly, and then things slow down, and they slow down at about an exponential rate, which is really unfortunate. But the good news is the more passwords you find, the less that are unfound and the more forks you can use. So when I was done with this, I was running about 31 or 32 forks in parallel. That was the limit with the amount of RAM I had. So I did a brute force attack of all the characters up to 9. So I found 3.6 million passwords that way, and it took 4 days. And then I had 811 million found passwords, which is a good number. So I started using that dictionary of found passwords. All dictionaries have different qualities, but these are all real passwords that I really found. So this is like the highest quality dictionary you can get. And using that dictionary and the standard John the Ripper rules, I found another 16 million passwords in 7 days. And you basically just wait for the stuff to slow down, and once it gets too slow, you say, I'm going to stop this because it would take years to finish. So the good news is it finds things quickly than slowly, and at some threshold that you get to, which for me was like a character a second, a password a second, I'm just giving up on this. So then I started to apply the rules twice on my 811 million found word dictionary, and yeah, it would take years to finish. So with the simple things like just doing a brute force attack on a dictionary, it would take like minutes or an hour to finish. But this applying the rules twice, the CPU usage goes up exponentially. So now we can run with 10 forks, and let's see, I was using the RockU dictionary, and I was down to 129 million unfound passwords. So I used a special rule that I wrote to replace a character with a control character. So if a password is password 123, I say, let's replace the first character with a control character. I ran through all the control characters. It's okay, let's replace the second character with all the control characters. And I found this when I was breaking my DES crypt passwords, that some passwords have control characters, and the standard dictionaries and the standard rules don't really look at that. So the good news, I have statistics on how many control character passwords I found, and there's a good number of them. So the second thing I did was, instead of replacing a character, was to insert a control character using the RockU 2021 dictionary. And I found another 8 million passwords pretty quickly with that. So these are the control character rules. So if you look at the optimized version, that's 1 line long, and that will do an overstrike of a control character in any position, no matter how long the password is. And it includes 80, which I believe is delete, if I recall correctly, and it includes all the standard control characters. So it's not very readable, but it's only 1 line long. And the rule to do the insert is the same thing. It's the last line, the optimized version. The unoptimized version still works, it's just not as fast. So I can deal with a 1 line rule. That's something I can show you and put on a slide. I can't put 3,000 line or bigger than that rules there. So here's Hashcat and Hashcat performance. So lower, upper, number, and special, length 7 took 3.7 days. That's not so bad. Then you go up to 8 characters, and it's 10 days. That's not so good. Then you have lower number passwords of length 9. That's 5.3 days. But the last one I ran was a lower number of length 10, 180 days. I found 2.4 million passwords. So that's really not a cost-effective thing to do. Sure. Okay. And you know, if you increase the length to 11 or something like that, you're pretty much hosed. And even if you have 10, 50, 90 GPUs, it's still not going to be a good day for you. So this is just not an efficient way of finding passwords. If you only have a few passwords, this might be a good way to do business. But when you have a lot of passwords, it's just not a scalable thing. So I pretty much gave up on Hashcat. After the thing that took 180 days, I said, I'm done with that. I turned the machine off. So here's some password statistics. This is the length of passwords. So, for example, passwords of length 1, 0% overall, 275. This includes duplicated passwords. And it goes all the way up to 30 plus. So this is really interesting because if you look at it, most of the passwords are like 8 or 9 characters long. And this doesn't show the password I couldn't find, but this is statistics on 869 million passwords. So this is pretty good statistics. I've not seen this anywhere else at a password talk. So I wrote my own program to generate these statistics. So this is, for example, like all lowercase was 18.9%. But then I have like all uppercase or all special characters. I just made these rules up. But the control characters will include Unicode stuff. So I got 269,000 passwords that had control characters. 8-bit ASCII is stuff where the most significant bits turned on, had 128,000 of those. But if you want to break passwords, statistically speaking, the lower digit stuff is 43%. So that's where you want to go to break your passwords if you want to get as much as you can, as quickly as you can. Just statistically speaking. I know your people's passwords, but I'm guessing most of them are going to be lowercase or lowercase in numbers. And again, based on 869 million found passwords. So now we have string classes. So all alpha is just alphabetic characters. So alpha number is alpha characters and then numbers after that. So that is 35% of all the passwords. So a password like password 123. But then we have like numbers followed by alphas, which would be 123 password. That's a lot less common. And I just made up more things, numbers, alphas, numbers, and all kinds of stuff. And I think this is very interesting statistic because this shows how people construct passwords. Obviously, these are not cryptographically strong random passwords, but these numbers don't add up to 100%, but I got a lot of passwords this way. So if you wanted, you could make a rule that says, let's go find, 6 alphabetics, then 3 numbers, for example. And that's a whole lot faster than saying all lowercase and all numbers together. And again, statistically speaking, you'll do pretty well that way. Yeah. So here's the control characters. This is the fun stuff. I got 8 new lines. I'm sorry, 8 line feeds. Character turns, 229,000 of those. Horizontal tab, that's a tab character, 134,000 of those. Delete characters, 1,045. So these are all unprintable things. And yet, there's a good number of these in passwords. I don't know how they put them in. I don't know how they got through whatever password screening process they have. There's a fair number of control characters. And these all came from my custom written rules to find non-printable characters and passwords. Do you have a question back there? Speak up a little bit more. Speak up, I can't hear you. Yes. So that is a possibility. So the question was, is the password I found could have been a collision with a real password? So hashes can have collisions. And so if the real password is Happy Tuesday, but password 123 happens to have the same hash as that, there would be a collision and I could find an incorrect thing. So that would be unfortunate that I wouldn't get the true password, but I would have a password that would generate the same hash. And so if I was breaking into computers, I could use my collided password just as effectively. So the statistics would not be good, but the potential to cause damage with it would be 100% with a collided password hash. Does that make sense? Very good. So, defenses. Don't use NT-landman. Why Windows uses NT-landman, which is the fastest algorithm and doesn't have salt, I don't know. 1979, people invented salt. It's a long time ago. It's a long time ago. Why are they not using a slower algorithm than NT-landman? I don't know. Even MD5 is slower. You know, not that MD5 is cryptographically strong, but Linux is using bcrypt. Bcrypt is very, very, very slow. So, two-factor authentication, always a good thing. There's the stupid phone text message, which is crappy two-factor authentication. There's hardware security modules, such as a YubiKey or Google's Titan key or a PIV card that has built-in secure thing. There's a lot of two-factor authentications. So if you're doing something involving money, you probably want to have a two-factor authentication so someone didn't steal your money. Use cryptographically strong random numbers or random strings. If you use a password manager and it generates a 20-character cryptographically strong password, it's not going to be a dictionary attack. It's not going to be found by a brute force attack. You saw how long it took to do a brute force attack. You know, pick your favorite length that you think is good, but make it more than 8 characters long. So I wrote a cryptographically strong random string generator in Python. These are some examples. It shows the number of bits of entropy. So I don't use any of these passwords, but I can generate these things and I can make them whatever length I want. And I can tell you only use numbers, only use uppercase, or only use whatever. And I can make 30-character passwords if I want. So is this better than a password manager? Absolutely not. But I wanted something that was simple and portable and quick. And I wrote it because it was only, like 50 lines or something like that. But none of these passwords are going to be in any dictionary. You're not going to be able to remember these, so you're going to need to use a password manager. I like local password managers. I don't want a password manager in the cloud because I don't want to worry about data breaches. KeePass is an excellent open source password manager. You can write your own. There's a whole bunch of good open source password managers. You can even host your own. I forgot what it was called. There are things that you can host yourself that run in your private cloud to do this. But I can't memorize these passwords. Maybe some of you folks memorize one or two, but I use a separate password for every different system. I probably have 200 or 300 passwords. I can't remember all that stuff. And what's better is that you can't torture me and I can't tell you the password because I don't know. So if you're using a GPU, you're going to want to undervolt it and underclock it to reduce its power consumption. Less power, less heat, thing will last longer. Some underclock better than others do. I could get like 10% power savings, which is still good because the thing ran a couple degrees cooler. There's some random links here. The open wall guys are the John the Ripper. there's lots of good sources of password information. Here are the dictionaries that I was using and how big they are. Some of these are good and some of these are bad. But like WeakPass, 37 gigabytes. Rocky 2021, 98 gigabytes. These are not small files. If you want to throw them into an editor, you better have a lot of RAM, or you better split it up in little pieces. Some of these are good, some of these are bad. I like RockU. It works well for me. It's shown high quality stuff. But get yourself a fair amount of storage if you're doing this. Is that the last slide? Maybe that's the last slide. Any questions? I believe we're going to get a microphone for people to ask questions. Anybody?
Hi, since you noticed such a large improvement using that specific word list,
Yes.
I imagine you were curious and went and investigated how they had come up with it in a way that was different enough to get that large of a difference. What did you find out?
So I don't know where the provenance of it, but it's allegedly from a data breach of RockU in 2021. So they claim that it's an actual leaked list of passwords. And statistically speaking, I was getting a lot of good data from that as opposed to other stuff. The very best dictionary I was using was the one that I found, my 900 odd million password thing. But I found all those passwords. They were real passwords. And when you start applying the rules to already found passwords, you get pretty good performance. But I don't know where Rocky 21 came from. They say it's from a data breach.
Well, I guess what I'm wondering is, do you believe that that's just unmodified results of that breach, or do you think that there are transforms applied to that to produce given the size?
I don't know. I'm guessing that it's a raw breach, but I don't know. But the thing is, applying transforms, you're going to, I mean, if you just like uppercase the third character, you're going to double
Right.
the file size. If you say uppercase one character, in each position, you're going to multiply the thing by like a factor of 10 or 20. So
anything that would be like a reasonably straightforward rule, you would expect to have someone just implement
yeah,
as a rule.
and you would
rather than-
increase the size of your file. So instead of uppercasing, what do you subtract? You substitute a number for a letter. So you have 10 characters. That's going to, each character position is going to multiply the size of your file by 10. So if you have, length 10 passwords, that's going to be 100 times bigger file. So I doubt that people augment the raw results with different rules, because that would just increase your file size. Like the last example would be by a factor of 100, which really sucks. Nobody wants to download a file 100 times bigger than they have to.
No, it seems to make sense. Thank you.
Thank you for your talk. I have a small question. Would you find that mutating the passwords and generating a new dictionary is faster than mutating the passwords in memory using rules?
So I believe that they do things more or less sequentially or possibly in a batch mode. I don't think there is a way with John the Ripper to apply a rule and write the whole file out. But I think that'd actually be slower. I think you'd be limited by I/O speeds as opposed to reading the thing in and just doing it in memory. I presume since each thread takes like 10 gigabytes of memory.
No, what I meant is if you had like a pre-processing stage where you took the rules that you found and you created a new dictionary before running JTR, would that have helped running things more efficiently? Or is it more efficient to run those rules in memory on existing inputs?
I think it's much more efficient to run them in memory on existing inputs. I think you'll simply multiply the size of your dictionary by pre-processing it with the rules by a factor of 100 or 1,000, and I don't have that much disk space.
Thank you.
We got a whole bunch of questions. He's got some there, a couple back there.
You gave a lot of examples of the formats of the passwords. I was curious if you did any analysis or had any data on the say longer passwords, like 12 or 16 characters or longer, if those were just combinations of words, or like what was the complexity of the longer passwords that you found?
I didn't look at that. But the problem when you've got like 12 character passwords, so I've got, what is it here? 50 million of them. I can't look at 50 million passwords and get statistics from. I could have written a program to see what they look like, but I didn't bother with that level of detail. The thing is, there's very little people that do statistics on the password count. I could write something so for characters, longer than 10 characters long, try to get some statistics on how they're formatted, but I haven't done that yet. It's certainly interesting future work.
So, just a question. You've got a pretty good corpus of data here.
Yes.
That you've built up. Is there any opportunity to use machine learning or AI, as we call it now, to use that to inform for creation of better rules and better mangling to, in essence, speed things up?
I would guess the answer would be yes, but if you have to feed in 869 million passwords into a LLM.
Well, no, you would create a new model at that point. You wouldn't use an LLM. But I guess what I'm saying is I wonder if those patterns, if run through several models and layers and the tensors, if you would be able to come up with some, call it groundbreaking rules for that mangling.
I am certain you could find some interesting rules. I don't know how groundbreaking they would be, and I don't have the resources to do this AI processing on it, but I think that's excellent work. And now that LLMs are becoming more of a thing, I think it's going to be the future of password cracking, because obviously you want good rules. And right now we say, okay, let's insert a character, or let's insert 2 characters. And you want to know which characters you want to insert. I mean, maybe vowels are good to insert. Maybe numbers are good to insert. Maybe tildes are good to insert. And I don't know what the good characters are, but presumably an LLM could figure that out.
So a follow-up question, do you have a GitHub where you posted all these goodies?
I do not. These are relatively large files, as you would imagine.
Well, more your rules and process.
The rules, so the one custom rule I wrote, I have on my slides. The other rules are John the Ripper rules. The only one that's an unusual rule, it's in their list of rules, but they have something they call OI2, which is insert or overstrike 2 characters. They have an OI1, but the OI2 found a bunch of passwords for me. But it's in the standard John the Ripper distribution. So the rule, let's see. Do I have the rule here? I'm sure I do. Yeah, so these 2 rules are the ones that I wrote myself. The good news is the guy in charge of John the Ripper is a guy named Solar Designer, who's a Linux security engineer, and he optimized these for me. I don't really understand the syntax of the stuff, but they work. And it's 2 lines, so anybody could write down those 2 lines and get the insert or overstrike of control characters. And I asked them to put in delete in there, so that's what the 80 is. That's hex for delete. ASCII 127, I believe. But
Okay.
it's certainly an interesting question.
Yeah, no, thank you.
Anybody else? We got a microphone.
As a quick one, did you explore, since you looked into GPU acceleration, did you explore alternative hardware, FPGA hosted stuff like on a big Xilinx part or something like that?
So John the Ripper has some acceleration for a really, really, really old FPGA. I think it's like 8 or 10 years old. And these things are hard to come by, and they're not nearly state of the art. I don't know of any current password cracking people that are using modern FPGAs. But in terms of price performance or performance per watt, an FPGA is going to beat a GPU. The thing about GPUs is they're made at huge scales, the prices are driven down by volume, and gamers' love of 4K 100 frame per second video games. So it's good for people cracking passwords like me. But it's never going to be as efficient as an FPGA.
Thank you.
have an assumption that you know a lot about hashing in every flavor. What do you like? You like Argon, Blake, for a modern hash?
So Bcrypt or Argon are state-of-the-art algorithms. So they're both nice and slow. They're both cryptographically very strong. Let's go back here. I don't think I have Argon listed here, but it's a modern encryption or modern hashing algorithm. So the thing is, if you look at NT-Landman, it is so weak. And you know, Microsoft came out with Windows 7, they came out with Windows 10, they came out with Windows 11. Surely they could have picked a better hashing algorithm. Surely they could have implemented 12 bits of salt or 36 bits of salt or some reasonable amount of salt, and they haven't done that. So why their hashing is so fast and they don't use salt, I have no answer for. Maybe Bill Gates or the current guy running Microsoft could tell you that, but I certainly can't. But I mean, look at Bcrypt. Bcrypt, it's 13,000 hashes a second. And look at NT-Landman. It's 41 million hashes a second. I'm sorry, 41 billion hashes a second. Why make it so easy for people like me? Why make the hashing algorithm so insecure? I don't have an answer for that. It's certainly inexcusable. It's certainly that they knew better. You know, oops. 1979 is when salt came about. 1979. It's 46 years ago. It's a long time. Even if it takes them a decade to implement this, they should have done it, you know, well before 2000. I don't know why they're not doing it. It's not a new idea. Sure.
On your slide there, I saw WPA2. Have you played with cracking WPA3? I mean, it's got some defenses, but
I have not.
okay.
So the reason I use the NT-Landman version of the Have I Been Pwned, it's the fastest algorithm. Why? So I think they also had, I don't know what it was. I think it was maybe it was SHA-1. I think I could get the passwords in SHA-1. But why should I pick SHA-1, which is so much slower, when I can pick NT-Landman, which is super duper fast? I want to crack passwords. I didn't want to melt CPUs and, you know, use gigawatts of power. So I did this all on my main computer that's sitting in my house. Right now it's getting like 15 or 20 passwords a second. And it's going to slow down, but that's not so bad. That's with 10 threads. When I get home, I'll probably take all the found passwords and make my unfound passwords substantially smaller. Probably increase the number of threads by 5 or 6. I mean forks, not threads. So they're actually separate processes forked. Thank you all for coming.